Welcome everyone to our first seminar series from the Early Career Committee of the Atmospheric Science section of the American Geophysical Union, because we love all of our acronyms to be squished together. My name is Benjamin Nault. I'm the head of the Early Career Committee, and I'm thrilled to introduce the start of this new series that we are doing to help early career scientists to get their names out there and show off the research that they're doing. We know the last couple of years have been especially hard for early career scientists to show off their research because of conferences being delayed or only in person. This is one way we're helping with that. And this is one of many things that the Early Career Committee of the Atmospheric Science section does. We do a lot of work on professional development, diversity, equity, and inclusion, and resources. If you're interested to learn about more, feel free to reach out to us. A person will put in the chat what our email address is. We'll also be at the fall meeting so that you can find us and talk to us. And with that, I'm going to turn it over to Gad to introduce our speakers and moderate the session.
Okay, good afternoon, everybody. I'm Gad Levy, and I am going to introduce, we are going to have 3 speakers tonight. Each one has 12 minutes, and then we are going to have some time for questions, and then we'll have some announcement at the end. I want to introduce the first speaker, Dr. Yi Zhang. Yi is a Miller postdoctoral fellow at UC Berkeley, and she received her bachelor's degree in physics from Peking University in 2016, then went to Princeton to study atmospheric and oceanic sciences, where she received a PhD in June of 2021, supervised by Stephen Foglis-Taylor, and her PhD work focused on tropical dynamics, convection, and radiative transfer. And then currently she has switched from the tropics to the extratropics, and she is a postdoctoral fellow at UC Berkeley with Bill Booth and working on mid-latitude heat waves. She's going to talk about an upper bound for extreme temperature over mid-latitude land. Yi, floor is yours.
Thank you, Gad, for the introduction. I'm very excited to share with you my recent work. So this work is inspired by the spectacular heat wave that happened over the Pacific Northwest region last year in June. And here you can see that the temperature of this heat wave stands out from the climatological values and broke the previous record by a huge margin of 5 Kelvin. And we also know that there have been multiple heat waves around the world this year that have broken previous record. So all these extreme temperatures led us to ask the question, what controls the maximum surface air temperature over mid-latitude land? Or in other words, can surface air temperature go up indefinitely? So let's start with a schematic of the temperature evolution during a heat wave. There are multiple drivers that can increase the temperature during a heat wave, but they largely fall into 2 groups. One group is what happens in the atmosphere, usually is an anticyclone, and the subsidence in the anticyclone heats the air adiabatically, and when the air reaches the surface, it arrives at a very high temperature. Also, the subsidence prohibits the formation of clouds, and therefore the insolation can hit the surface directly. And the second group is the land surface processes, especially the soil moisture atmosphere feedback. So if the soil moisture is dried up, and the sensible heat flux will increase at the expense of decrease of latent heat flux, and then the sensible heat flux then can warm up the surface air, near surface air even more. So that forms a positive feedback loop. However, very little attention has been paid to what terminates a heat wave, and that is going to be the focus of this talk. So the hypothesis is that the surface temperature cannot go up indefinitely during a heat wave, because if you heat the bottom of a fluid, at some point it's going to be convectively unstable. So the boundary layer air will go up, and then and it condenses, and water vapor condenses, and then it rains, and then the surface temperature drops. Here is just a vertical schematic of this hypothesis. An anticyclone comes in, lifts the free tropospheric temperature, raises the first free tropospheric temperature, and forms an inversion at the boundary layer top. And then the other processes, land surface processes, and insolation, other processes can heat the surface, the boundary layer air up. And at some point, the boundary layer, the dry adiabatic boundary layer is neutrally stable with respect to the free troposphere. And then this temperature is the maximum temperature that can be achieved during a heat wave. So here I'm showing some observational evidence for this hypothesis. These curves are composite time series relative to the annual hottest day for each location over mid-latitude land, and then I took an average of all locations. So the red curve is surface temperature. There's strong diurnal cycle, and by construction, it peaks at lag 0. And the black curve is convective available potential energy, which measures the instability to convection. It also peaks on day 0, meaning that the hottest day is also the most unstable day to vertical convection, And then the precipitation picks up right after the annual hottest day. So the instability increases, and then it rains, and once it rains, the surface temperature drops. This time series justifies the hypothesis. And based on this hypothesis, we can then write down a theoretical upper bound for the surface temperature. We use a very simple criterion for convective instability or convective stability, which is surface moist static energy should not exceed the free tropospheric saturation MSE in order for the heat to be built up in the boundary layer. And moist static energy's definition is listed here. It contains 3 terms: temperature, humidity, and geopotential height. So we expand the inequality, and the left-hand side contains 3 terms of the surface, the right-hand side, the 3 terms of free troposphere, and where we use the 500 millibar level to represent the free troposphere. So the first term on the right-hand side is T500. The second term, the saturation specific humidity, is also a function of T500 only. This is just Clausius-Clapeyron relationship. And the third term, geopotential height of 500 millibar, can also be approximated as a linear function of T500. So therefore, we have the right-hand side just a function of T500 only. And then we look at the left. So since we are interested in the upper bound, the humidity goes to 0. Therefore, all the available moist static energy can be allocated to temperature. And this Zs is the surface elevation, which doesn't change with time. So put everything together, we have this upper bound for surface temperature, which is just a function of T500. And now we test whether this theoretical upper bound works for the observations. The y-axis is the surface temperature plus the contribution from surface elevation. Therefore, we can compare all locations readily. And then the x-axis is T500. The theoretical upper bound indicated by this equation is the dashed line. Above this dashed line is definitely unstable and therefore impossible. So the reanalysis data lie right beneath this upper bound. And we also look at the observations. There's there's satellite observation of T500 and ground station observations of surface temperature. The joint distribution from the observational data also lies right beneath the theoretical upper bound. And this shows that this upper bound is quite accurate. So with this, we can take a look at what happened during the 2021 Pacific Northwest heat wave. Which we first take a derivative of the upper bound with respect to T500, and we result in 3 terms. The first one is the temperature term, which is a constant. And that means if T500 increases by 1 Kelvin, the surface temperature can also increase by 1 Kelvin. The second term is the Clausius-Clapeyron term, and it varies wildly with depending on which T500 you start with. And the third term is the geopotential term, also a constant and rather small. So on the right, I'm showing the same diagram, but only with data points over the Pacific Northwest region. The gap of distribution of the data between the gap between the distribution of the data and the upper bound is because this region is not completely dry. And this arrow links the previous temperature record to the new temperature record. You can tell that the direction of the arrow is roughly parallel to the upper bound. So using this equation and plugging in the numbers of these actual heat waves, the previous record has a T500 of 266 Kelvin, and the difference between the T500 of the new record and previous one is 2.2 Kelvin. So we plug in these numbers into the equation above. We get that the temperature term contributes 2.2 Kelvin to the surface temperature, and the Clausius-Clapeyron term contributes 1.8 Kelvin, and geopotential term contributes 0.5 Kelvin. The total is a 4.5 Kelvin surface temperature anomaly, which almost explained all the 5 Kelvin temperature anomaly of this event. So coming back to the well-known drivers of heat waves, one is anticyclone, the other is soil moisture atmosphere feedback. What are their roles in heat waves within our framework? Here I'm showing, using the color shading shows the 500 millibar relative vorticity, which is a proxy. You can think of it as a proxy for the strength of the anticyclone. And the gradients is mostly horizontal. So stronger anticyclone means higher T500. But given a certain T500, there's little dependence of the strength of the anticyclone on the surface temperature. So that means if you have a strong anticyclone, it's not guaranteed that the surface temperature is going to be very high. It could also be very low. And the second panel shows the surface soil moisture. The gradient is mostly vertical. So the drier the soil is, the closer the actual temperature is to the upper bound. So here's our schematic for heat waves, and we put everything together. A stronger anticyclone pushes the data points to the right. It increases surface temperature by raising the upper bound of surface temperature, and the drier soil will allow the actual surface temperature to approach this upper bound. So now we have a more complete picture of the processes involved in heat waves. In addition to the previously known drivers, anticyclone, soil moisture, this work demonstrates the importance of convective instability in halting the development of heat waves. And with this hypothesis, we provided a theoretical upper bound for surface temperature, which we can use to understand the interaction between atmospheric dynamics and land surface processes. And we can also quantify the contribution of different drivers of individual heat waves and even project future increases of extreme temperatures. So this work is now in a preprint, and if you're interested in related papers, there are other papers on how convective neutrality determines the maximum heat stress or maximum temperature. These are some papers that might be of your interest. So I'll stop here and take questions. Thank you.
Thank you, Yi. Any questions? Where do I see the questions?
They will be in the chat. So if you look in the sidebar of the program, you'll see a chat option and push it down, push the arrow down.
Oh, I saw a question from Eliza.
Okay. I'm still looking for it though.
The question is, have you tested this methodology on any other heat waves in other parts of the world? Yes, in the preprint, we tested this with the Western Europe, the heat wave in Western Europe in 2019, and the Russian heat wave in 2010. And this framework worked pretty well. And it looks similar to the Pacific Northwest heat wave. But the contribution of soil moisture and anticyclone, the partitioning between soil moisture and anticyclone is different.
I have a question. How much predictability would you have for predicting when the well?
Sorry, how much
how much predictability does that give you?
Oh,
if it does.
Okay. This is also related to the second question in the chat box. So should we expect the strength of heat waves in the future to scale with the rate of change of T500? Yes, so with future warming, we can play the same game as the Pacific Northwest heat wave. Take the derivative of the equation and we have these three terms. And we take a T500 at 262, which is the most common T500 on the annual hottest days over mid-latitude land. And this gives us a total of 1.86. So the temperature term contributes to 1, Clapeyron term 0.65, and geopotential term 0.21. And that means if T500 increases by 1 Kelvin, then overall the annual maximum temperature will increase by 1.9 Kelvin, and it is also consistent with what we have observed over the past 4 decades.
So follow-up questions during an actual event, heat wave, can you predict when it will end?
So this theory only tells us what the maximum temperature of this event, but it doesn't tell us when it ends.
Okay. Right. Just an idea to try and put in a function, a time-dependent function.
Yeah,
I think our time, unless there's another question, it's time we should move on to the next speaker. Thank you very much, Yi.
Thank you.
And is the next speaker Victoria? Oh, no.
Yes.
Okay, Emmanuel. So Dr. Emmanuel Akilabi is a postdoc at Boston University. He is interested in boundary layer meteorology, turbulence modeling, and large eddy simulation. His current research focuses on the role of coherent structures in scalar transport in atmospheric boundary layer flows over heterogeneous landscape. And he is going to talk about the relevance of dispersive fluxes within and over real urban canopy, a large eddy simulation study. Take it up.
All right, thank you. Okay, I can share. Trying to share my screen. Sorry, I couldn't find the show sign anymore. Oh, okay. Thank you. So thank you very much. So my name is Emmanuel. I work at Boston University, and this is work I did with my advisor, Dan. So I got this paper from this from this website from United Nations that more than half of the world's population now live in urban areas, and the effect of this means that it's going to change. It's probably going to affect the urban climate. But before I go into details, I would just like to just show you some of the layers we have within the urban boundary layer. So basically, I will just focus on we have the inertial layer, which is a region where
Emmanuel,
hello?
sorry, you're still on your first slide. It didn't change. Sorry to interrupt you.
Okay, it's okay.
Okay, now it's switched to the introduction slide.
All right. Okay, can you see my slide change now?
Yeah, it's on the introduction slide, the UN news one.
Oh, okay. Can I share again? Maybe
Steve, minimize what, yeah, share again, because right now we're seeing the PowerPoint, not what the actual display,
all right.
We're still seeing just the PowerPoint, not what you're displaying. So you're going to have to try to minimize the PowerPoint itself.
Okay.
Or move it to the side.
So can you see my PowerPoint now?
We're seeing it in non-presenter mode.
Oh. Okay.
Perfect.
All right. Okay, good. Sorry about that. So I was talking about, so the inertial layer is simply a region of the flow where the influence of the urban canopy at the bottom is not felt. It's negligible. While as you move closer to the surface, you have a region called the roughness sublayer, which is the turbulence here is strongly influenced by the topology of by the urban morphology, sorry. And so the presence of this canopy for forests or human activity have a big influence on urban climate. And I mean, even in the last presentation, she talked about heat islands. Basically, most of this we have what we call urban heat islands, which is mostly reach a time which is mostly when you have the temperature within the urban area is higher than its surrounding environment. And in order to understand this or capture some of these effects, numerical weather prediction is usually used, but this is limited because the weather predictions models cannot capture the complexity of turbulence within the urban areas. And so these turbulent motions needs to be parameterized. And so one of the things that needs to be parameterized, which is mostly ignored in most numerical weather prediction, is the dispersive flux, which I'll be talking about. And so if we take the momentum equation and we look at the unknown term, which is a stress tensor, you can divide it into the turbulent flux, the dispersive flux, and the viscous stress. The turbulence flux have been studied mostly, and I think it's adequately parameterized. But most times the dispersive flux is ignored, and it's been regarded as one of the most poorly understood terms in the double average momentum equation. And so just because for short time, I'll just focus on these two objectives. First, to look at how important is dispersive fluxes in real urban canopy using large eddy simulation. And secondly, what is the effects of temporal and spatial averaging? So to calculate dispersive flux, especially for numerical weather prediction application, it's important you apply temporal averaging, and then you also apply spatial averaging. So what is perform some sensitivity of temporal and spatial averaging on dispersive fluxes. So the model used is the large eddy simulation model, which simply just solves the Navier-Stokes equation. And each of the very U here is simply the filtered velocity field. The model applied discretized the entire model domain using finite difference. It also uses staggered grid in this form. Because we also have urban canopy, when we have to explicitly resolve the buildings, the urban topology is simply implemented this way. So areas where you have an obstacle or a building, the value of velocity is changed to 0, and then we apply a constant flux model to account for the presence of the buildings within. And so the urban canopy we use, the data set we're using is an area in Boston. It's very close to the Kmart Square. I don't know if anyone is familiar. So if you look at the south western region, is home to hospitals with I'll say average height of about 70 meters. And towards the northeastern part is the business districts, where you have very tall buildings. And the tallest building is around 227 meters. The mean building height is about 19 meters. And the standard deviation of all the building height is about 17 meters. And so to look at the setup, because we do not want the turbulence coming from west to east, we do not want the influence of the building structures on the turbulence to be transferred back to the inlet. Most studies like this use periodic boundary condition, and because we do not want that situation, we decided to create a different kind of boundary condition, non-cyclic boundary condition, especially in the x direction. So we applied what called the turbulence recycling technique. The process is simply we run a precursor run, which is simply homogeneous isotropic turbulence. The result of the precursor run is copied multiple times. So the domain of the precursor run could be smaller than the main run. It's copied all over the main run, and this serves as like the initial condition. And then at every time step, the fluctuations are taken at the end of the recycling region, see here, and the fluctuations are recycled to the inflow, and the profile of all the variables are simply taken from the precursor run. And so at every time step, you see as the flow goes towards the urban canopy, we're able to study the turbulence within the urban canopy. And so in order to properly resolve the flow within the urban canopy, we created two different domains. So the main domain, which is called here the parent domain, And then we have a child's domain, which is only restricted within the urban canopy. And so the boundary conditions of this parent domain is simply taken, of this child domain is taken from the parent's domain with just one-way nesting. So that means that the effects, the parent's domain do not take any information from the child's domain. And so some of the parameters here is the parent's domain is really large, about 13 kilometers. I mean, for an LES, I would say. Also, the grid size for the parent domain is 8 meters, and that for the child's domain is 4 meters resolution. And these are some of the boundary conditions and parameters used. So to start with, so first I try to show the difference between the dispersive flux and the turbulent flux, which it's very familiar. And so here I'm presenting the ratio between the dispersive flux and the sum of turbulent and dispersive flux. So on initially at the beginning, I told you that the height, okay, maybe I might jump. The height of the roughness sublayer is usually regarded as between 2 to 5 times of the mean building height h. So that's why I put it in gray here. And you see that the dispersive flux within this region and even above this region, dispersive flux can be about 15% of the total flux. We also did the same for scalars also. I would say for scalars, it's a little bit smaller, so between 10% to between 5 to 10% within this region, and also like above it. And so then with my second objective, I'll look at the sensitivity of temporal and spatial averaging. And so first we started with a very small temporal averaging, which is 5T. 5T here corresponds to less than 1 minute of averaging, so which is really small. And you see that the dispersive flux is really large in this situation. And we also observed that to increase the temporal averaging, the profile actually converges so the 200 or 200 T is roughly around 3 hours of averaging. And also there is also a very strong sensitivity to spatial averaging. So what we did was in the child's domain that we have, we decided to just average over half of the domain and also a quarter of the domain just to see how the profile will change. And you see that there is also very strong sensitivity to how large the averaging is. So it seems that the larger the averaging, maybe the less important the dispersive flux might be. And there are also other factors that also determine how important dispersive flux, different from the spatial averaging. But for now, we just restrict it to this. Also, there is also the morphology, the parameter of the urban canopy. So also you have the plane area fraction and so on, which have been looked into by other studies. So here, which is also important, is that if we look at just if we look at the distribution of both the turbulent flux and the dispersive flux, you see that there are regions, especially around high-rise buildings. You see that the dispersive flux can be one order of magnitude larger than the turbulent flux, and that's extremely important. This shows that it's also very important to parameterize dispersive fluxes. So in conclusion, we see that dispersive momentum fluxes can be significant, and they are also very sensitive to temporal and spatial averaging. And the dispersive fluxes can be spatially heterogeneous and enhanced by the presence of high-rise buildings. And so this work suggests the need to parameterize both turbulent and dispersive fluxes, especially in regions in real urban canopies and in mesoscale models. And so the future work is to look at the effect of stratification. So for this study, we only look at neutral stratification. Also to look at budget equation, which is sometimes mostly used as to close the momentum equation in numerical climate models. And also with these two information, we can develop and improved urban canopy parameterization. To acknowledge some of the sponsors of this work. For more details, this work has been published in Boundary Layer Metrology, so you can take a look. Thank you very much.
Thank you very much, Emmanuel. I'm looking for questions. I don't see any questions, do I? No, I don't see any questions. I have a question in terms of your conclusion about the averaging scale. Do you have any practical conclusion based on the fact that the longer the averaging scale, the less you see that, which it makes a lot of sense, but any other comments?
So my applicability would be, so for in the more you resolve, so if the resolution of the numerical weather prediction you're using is smaller, I mean, let's say it's of the order of, let's say 100 meters or 1,000, close to, let's say 1,000 meters, then I think it's important to account for dispersive flux in that case.
Okay, and now I see another question from Gunnar. It seems you selected a very low roughness length, but you skipped fast, so could not get the details. Could you repeat that? Can you explain that?
Oh, okay. So because I'm using LES in this case, so I'm resolving all the building, and based on the grid resolution, which is about 4 meters. So the roughness length is simply to account for things like cars, small trees that is not explicitly resolved in the simulation. And so there is a relation to determine what your roughness length should be. I think it's about 0.1 of your of the smallest grid size we're using, especially close to the surface. So in this case, my first computational level will be 2 meters. It's simply half because I'm using staggered grid, which is different, and that's why I use this very small roughness length.
Okay, thank you. There's a question from Srinath Patel. I was wondering, why do you think large scale contributes to lesser dispersive fluxes? Because one would expect larger averaging scales would include the lower frequency fluxes.
Sorry, can you come again? I don't understand the question. Okay, larger scale contributes to lesser dispersive fluxes. Why you think larger scale contributes to it? No, okay. Now the dispersive fluxes here are so this is looking at it on a small scale, so it's an LES, and so like in this model, actually we have a mean flux, which is something that's already resolved in numerical weather prediction. Okay, so maybe I don't understand the question properly, but I don't think the large scale will influence the dispersive flux. So the dispersive flux is simply due to the heterogeneity of the urban surface, of the surface. I hope I'm able to answer the question.
Okay, there's a question again from Gunnar. There's 0.1 of average building height urban roughness length is usually around 1 meter. I would interpret it, why do you use 0.1 when urban roughness length is usually 1 meter?
Okay. So for this simulation, so like I said, it also depends. So what you use as a reference length strongly depends on the resolution that you're working on. And so there is this, I mean, we can talk more about this later, but there are papers that shows this relationship between the resolution of the simulation with what roughness length you should use.
Okay, I think we should move on and to the next speaker. And the next speaker is Victoria Schoenwald. Victoria is a fourth-year PhD student at the University of Miami, working with Dr. Ben Kirtman. She received her bachelor's degree in biology from Sacred Heart University in Connecticut, and is currently studying sea level rise along the east coast of the United States and its connection to large-scale atmospheric and oceanic circulation. And she is going to talk about understanding sea level rise acceleration along the east coast of North America. Victoria?
Hello. Okay. Hello, everyone. Thanks for having me come on this seminar series. As said before, I'll be talking about sea level rise acceleration along the east coast of North America. So here's a brief summary of what I'll be going through today. And first, I wanted to motivate this research and why sea level rise is important with regards to protecting our coastal cities. This picture on the right-hand side is actually taken from Miami, about where I live. And as you can see, flooding affects us a lot during the year. So this topic is especially important to me. I'll go through some goals and research questions, and then our methodology of using empirical mode decomposition, and we'll go through the results and some future work. So coastal flooding on the east coast of the United States has prompted many studies due to sea level rise rates accelerating faster there than the global average. And this is partly due to land subsidence. And many also believe that the proximity to the tail end of the Atlantic meridional overturning circulation is also to blame. As you can see in these plots above, after 2000, nuisance flooding, which is what the blue bars are showing, also known as sunny day flooding, has increased dramatically in the last couple of decades. And nuisance flooding can occur with even weak storms or normal high tides or spring tides. And this is when the normal normal sea level is being pushed beyond the threshold without like a major storm or hurricane or something like that. But these flooding rates are not equal across the East Coast, and previous studies have looked at regional differences in the coastal flooding and sea level rise acceleration. One study done by Ezer in 2019 looked into this regional difference along the East Coast of sea level rise and coastal flooding and its connections to large-scale atmospheric and oceanic circulation. He found that before 2010, sea level rise was accelerating in the mid-Atlantic bight in this area north of Cape Hatteras, North Carolina. And this was attributed to a weakening in southward shifting Gulf Stream. And then after 2010, sea level rise acceleration in this region started decelerating, while south of Cape Hatteras down to Key West, Florida, the sea level rise rate was accelerating there. And this was attributed to a slower moving Gulf Stream that had shifted northward, as well as a warming trend in the Florida current. The main findings from this research suggested that variations in the Gulf Stream or winds could be responsible for the differences in the mid-Atlantic bight and the South Atlantic bight. And these Gulf Stream variations could also be connected to basin-wide changes, such as variability of ENSO, the North Atlantic Oscillation, and AMOC. These accelerations have been termed hotspots of sea level rise, and these hotspots occur when sea level rise rates are 3 to 4 times the global average, and they can migrate meridionally up and down the coast. Therefore, it is important to determine when and where these hotspots will occur so we can better inform coastal cities of their flood risk. Another study done by Volkov et al. In 2019 suggested large-scale processes linked to coastal sea level variability, and they reported that the leading mode of interannual sea level variability in the North Atlantic represents a tripole pattern, with the subtropical band varying out of phase with the tropical and subpolar bands. And this SSH tripole variability is largely due to meridional heat divergence influenced by AMOC, and stronger meridional heat transport favors higher thermospheric sea level in the subtropical band 1 year later. So this hints at a potential for multi-year predictability of sea level using ocean heat transport. So in order to investigate the larger scale circulation and its connection to coastal sea level variability on the east coast of the US, we wanted to compare 4 commonly used data sets in sea level rise studies in order to determine if coastal locations are being represented by the data well. So tide gauge data is often used in sea level rise studies, and these tide gauge stations are located up and down the East Coast and all over the world, but this is the region I'm focusing on. But most of the tide gauge stations that I'm looking at are located within bays and inlets, so therefore we wanted to make sure these coastal locations are capturing the global signals for large-scale atmospheric and oceanic circulation. And then we also wanted to break down the sea surface height time series from different data sets in order to see how the different parts of the climate system are contributing to large spikes in sea surface height. For this study, I chose to look at Charleston, South Carolina, mainly because it's at a key location for coastal flooding, and I will look into other sites later on, not in this presentation, but in other research. And then lastly, we want to see if sea surface height data from the tide gauge stations will be accurate in predicting coastal flooding. So the method that we used to analyze the sea surface height data was empirical mode decomposition. And we chose this method because there are a number of atmospheric and oceanic phenomena influence sea level variability, and they occur on a variety of different timescales from days to decades. And empirical mode decomposition breaks down that signal into different frequencies, starting with the highest and then ending with the lowest or the trend. It is kind of like a low pass filter that is helpful for studying low frequency oscillations, which is what I'm interested in. So this technique was applied to 4 different data sets, including non-tidal residual data from the Charleston tide gauge station, and that data is the sea surface height with the astronomical component removed. And then the next data set was an NCEP reanalysis sea surface height, chosen at the point closest to Charleston to represent Charleston within that data set, and the same method with AVISA altimetry data and high resolution model data taken from the IHASP experiment. And after we took these 4 data sets representing Charleston sea surface height, we applied the empirical mode decomposition. And this is an example from the tide gauge data SSH after the EMD was applied. And you can see it's broken down into what's called intrinsic mode functions, or IMFs. And 1, the light pink color, represents the highest frequency, and then 6 represents the lowest frequency or the trend. And you can see the acceleration of sea level rise after about 2012 in this data, and then the other intrinsic mode functions contributing as well. So for this study, I wanted to take a look at the lower frequency IMFs of about greater than 5 years and correlate those with global sea surface height and surface current speed data from each of these data sets to see if we could see larger climate patterns. So these first plots are the low frequency IMFs from the tide gauge data correlated with global sea surface height and current speed data from the reanalysis data, which is the top two, and the satellite data in the bottom two panels. So in panel A, you can see that there's a large coastal signal as well as the North Atlantic SSH tripole really coming through. Whereas in panel C with the satellite data, the signal seems to be overwhelmed by the warming trend, but possibly hinting at the tripole pattern under Greenland up here, or maybe some other correlation south of Greenland. And with the current speed data, we can see a clear split in the Gulf Stream, north and south of about where a little north of Cape Hatteras, like we talked about in that other study. And this split in the Gulf Stream could represent possible shifting north and south and the variability of the separation point of the Gulf Stream. And the negative correlation south of Cape Hatteras could also mean higher sea surface heights at Charleston being associated with a slower moving Gulf Stream or possibly AMOC. With the satellite data, we can start to see a similar pattern, but it's not as clear because we think the trend is overwhelming that data. And we think possibly the reanalysis data is underestimating the trend. So the next step with this data would be to take out the trend from the reanalysis data. But the main takeaway from this is that the lower frequency modes from the tide gauge data are representing larger scale ocean circulation components that are affecting sea level rise. So these next plots are comparing the low frequency IMFs from the reanalysis and satellite data proxies for Charleston, and that is also correlated with global sea surface height and current speed data. And we're seeing the same types of patterns that we saw with the tide gauge data. We see the tripole resemblance in both data sets, as well as the Gulf Stream signal. And this tripole may resemble changes in the meridional heat transport by AMOC, as well as the warming Florida current. And the tripole has also been linked to positive North Atlantic oscillation in previous studies. And the Gulf Stream variability associated with the lower frequency IMFs leads us to question whether the Gulf Stream is part of a long-term trend or if the variability is truly a regional hotspot related to a natural variability. The last data set that we looked at was the high-resolution model data from the IHUSP experiment. And the sea surface height correlations show a similar pattern, but the signal is opposite in the subtropical band. And we also see signs of a Gulf Stream signal in the sea surface height data, but with the current speed data, we see almost no correlation. And this leads us to question why the signal is not the same as it is in the observational data. So even when we use the full historical and climate change record from the IHUSP data from 1950 to 2100, we still did not see results. And we know that models do not capture the Gulf Stream and the separation point of the Gulf Stream extremely well. So this could be a potential source of the differences we see between the data sets. So one question we had with the differences between was this trend at the end of the data sets. And if we look at the IMF time series from each data set, we can see where the differences in the correlations between the data sets might come from. So the top three panels are our reanalysis, satellite, and tide gauge data, and they all seem to have a trend at the end. But we're not seeing that same trend with the IHUSP data. And this is a shorter data set, only going to 2020. But even when I used the full IHUSP data set, I still did not see a positive trend at the end. So lastly, I wanted to take a global look using just one of the IMFs from the tide gauge data at Charleston, which had about a 5 to 7 year frequency, to see what climate patterns emerged. And this data was correlated with global sea surface height from reanalysis. And we can start to see a La Nina-like pattern in the Central Pacific that may be correlated with very low frequency ENSO or possibly a Pacific decadal-like pattern. And I do want to note that the higher frequency IMFs show more of a correlation with El Nino, but the correlation pattern was not as strong. So this motivates us to look at more variables and see what other larger climate patterns we see in the IMF correlations. And also in the Southern Ocean, we have this strong positive correlation, which we think maybe hints at an AMOC connection. And in recent studies, the tripole has been associated with the AMO, which has been in the warm phase since the mid-90s, so that could also be connected. So if we go back to our original research questions and goals, we can see that the tide gauge data is fairly representative of the global patterns, since we see similar patterns in the satellite and reanalysis data. And also with regards to large-scale ocean and atmospheric connections, we see Gulf Stream variability connected, the SSH tripole, and AMOC-like patterns emerging, leaving us to believe that there are natural variability components to these changing hotspots of sea level rise. As for the predictability question, we believe that one problem with the IHESP and reanalysis data could be freshwater input from Greenland ice melt may not be estimated correctly. And we also see a potential source of predictability with the Gulf Stream separation point, as well as meridional heat transport. So one future goal would be to see why the model data is not capturing the same trends as the observational data, especially with the Gulf Stream. So with that, I'll take any questions. Thank you.
I don't see any questions right now. We are kind of running out of time. I have one question or suggestion. When was your last point for future work? Did you try the other ones, the other models and sets that are consistent and do show an increase? Did you try and shorten the time series that you are analyzing for those and see if you see the same thing that you see in the data set that doesn't show this? That would be one possible reason, is just that you don't have long enough time series, and then if you use the same time series, you may be seeing a different trend.
Yeah, I haven't looked at other model data, but when we looked at the full time series from 1950 to 2100, we still didn't see a trend at the end of the data set. So we're still wondering why that isn't showing up, and we're looking into that more.
Okay, there's a question. Do you think higher resolution models or reanalysis would show the correlation more like observations, or do you think there are issues beyond resolution?
Well, the IHESP data is pretty high resolution, so we're thinking there is some sort of issue with a natural variability component not being captured in the reanalysis and model data. And we're thinking it could be the Greenland ice melt. Also, the IHESP data doesn't do a perfect job in representing the Gulf Stream, and we're thinking there is some variability where with the Gulf Stream moving up and down and off coast and more towards the coast. So we're looking into that too. Okay,
can I interpret that as saying that it may be resolution, but it's not only resolution?
Yes.
Okay. All right, I think we are out of time. I wanted to thank all the speakers. For everybody, I put in the chat, if anybody is interested in co-editing some special issues, please contact me. That's in general. Thank you. And if you have any feedback or suggestion, please email the earlycareeratmosphere@gmail.com.
Thank you, Gad. Thank you again for the speakers. Really great talks. We really appreciate it. If you enjoyed this series, please feel free to email us and let us know. If you have any comments or feedback on this, let us know. And we're also continuously looking for speakers in the future. So if this is something you really like, let us know and we'll continue doing this. And thank you for your time, Gad, and leading these great discussions.
Thank you. Bye.
Bye, everyone.